Okay, so I'm going to move on to certain parts of the chapter 8 again. I hope you guys keep watching the YouTube channel so you can keep up with the chapter 8. So the last time we talked about the hydration. So hydration simply means that you're going to surround the double bond with the like a water, H and OH. So it'll be, it's like you're gonna surround this one by those, so you have a hydration process over here. So the one we did for hydration was using water with the acidic condition at certain amount of heat. You can also put hydrogen and hydroxy group on the carbons and previously double bond. But there's another one we call oxymercuration. Okay. So in here, we're gonna do pretty much a similar process, but with the mercury 2 acetate. So we're gonna put this in this form. So please remember this one. Okay. So I'll give you one example here. And this is the one with the double bond for sure, right? And then this is what it looks like. If you have this is what we mean by mercury acetate here. Okay. So what happens to this one is they just break apart like this, and then it comes in the tag over here. Okay. So there's no more two, but just one here. So what happens to this one? Oh, by the way, you don't have to know the mechanism. I'm just doing this for the understanding, better understanding. But just whenever I do this, just focus on the products. What will be formed after this? So the only thing we really need to focus on in this process is the last product. Okay? Anyway, I'll do this. So if this is happening, double bond is gone now, right? Then have like this. Okay? So this is formed now. Okay? And then there's a hydrogen, hidden hydrogen over here. This is metal over here. Okay? So if this is happening here, they just go over here and drag this bond. So you can make a more stable carbocation over here. So they now stretch it out like here. And then this carbocation, now you have water comes in. And you're going to have this attack here. So this is the pair of electron now into the carbocation. This is what look for the. This is electrophile. This is a nucleophile. It kind of makes the bond there. So what happens to there is now you have this one, and now highly charged on it here. Okay. And then there's another water comes in. Grab this one, and then this goes on to this also. So eventually, you're going to have okay. So now you have the hydrogen group on this carbon here, but now you need to put the hydrogen. And this is where we use sodium chlorhydride. And then this is a really strong reducing agent. So this will make this one. Okay. And this will show you hydroxide as also making this one go. Then finally, you have a final product. It's like this. So the one thing I want you to kind of remember from here. So we have this one coming with the initially mercury 2 acetate, right? With the water, with the actually this is also with the organic solvent TSF. But normally I don't put, and then we have a very strong resisting agent. So if this was happening, we call this oxymercuration here. This will hydrate this double bond here. You see OH over here. It's like a water addition, pretty much. And then I just want you to remember this one. In this oxymercuration process, this is now you need to remember. When the hydroxy group will be on more substitute carbocation position here. So this is also follow Markovnikov rule. So the hydroxy, because usually you don't see this one here. So maybe on your exam you'll just see like this is your answer, because I normally show the hydrogen over here, right? So this is the final product. You see this hydroxy group on the most substitute position of the carbon cation position here. So it also follows Markovnikov rule here, where you can find the hydroxy group on the more substitute carbons. So once again, I want you to remember this one. When it has oxymercuration hydration, you're going to add water. So it means hydrogen and OH, hydroxy group. And we don't really show the hydrogens on the organic compounds in the skeleton structure. So the hydroxy group always going to position where you can find more substitute carbon. Kind of makes sense, right? This is what you actually remember. Okay. Makes sense? You good? So, all right. Do you have a question? We good? Okay, so we're gonna do one more hydration here. We're gonna call this hydroboration. So this is pretty much the same hydration works, but with a different method here. So I'll do the same. This one, but let's try to look at this one more top and side view. So I'm gonna draw more like this way. This is what you see that, right? You see that from here up, like a 45-degree on the top, you see. So you can see more this one. In this case, we're gonna use hydrogen oxide and some base here. Okay? So what you can do is try to use this borane first. Comes in. So they come in like in one face of this double bond here. So they come in this way. And what happens this one, they'll do some attack here and here. And also they kind of break this one over here. Okay? So they kind of make sort of a semi-breaking forming along with this carbon in the double bond among these two. Okay? So then what happens to this one is, finally, they just break apart right here, and they form this one, and double bond this one. Okay? So the reason why they're coming into this way is the methyl group over here. If you look at this one more precisely, this is actually what it looks like, right? So if the borane comes in this way, there will be quite of a static hindrance there, right? Because because the methyl group is kind of bulky with the hydrogen. So this is why the borane comes in this way, not this way. Okay, so then you have hydrogen added to on this side here, and you have a leftover kind of hanging here. Okay. So once again, just focus on the final product. I'll just show you the steps though. So you have a peroxide over here, but you come to the base over here, right? Base. So base, what they do is they attack one of the hydrogen here. It comes on this way. Okay. So that makes this one. Okay. Because the pair of electron now is onto this oxygen right here. Because of that, it's become water. So when it comes to this one, now this is going to attack over here. Okay. See, this is over here. Then what happens to this one is it becomes here. Okay. This is okay. So then this is the tricky part. You don't have to know. Just once again, this final product is more important. You remember first part of the chapter 6? One of the reaction was rearrangement. So the bond is rearranged to this one. Okay, so now it's become this way. Okay, it's because of the nature of the boron here. Boron is pretty positive with the electronegativity terms. So there was to be more stabilized by rearranging this bond to oxygen over here, giving this negative charge now on from here. And now it gets to this one. It goes to this way. The pair of electron, the bond between these two will go this way. So now you break this one. Now the negative charge is on here. It's gone. Okay. So now you have hydroxide anion attached to this one and goes on to this one. Okay. So now you have this is just gone, right? And then the okay, and then now you have water comes in, and you just need to have the grabs one of this, and that will make this one. Okay, so then you finally have this. Okay, so if I summarize this one here. In this case, you use chlorine, right? And you use the hydrogen peroxide and also base. Usually we use the sodium hydroxide. And then now you have this one. Okay, so you don't see it here, but there is this one over here, right? So that means, do you see this wedge? So it's kind of coming from this way, but those wedge lines are these dot lines are going backward over here. So this dash line goes backward, and together with these two, so you have a hydrogen group on the same face. So we kind of call this. I want you to remember this one. We call this syn stereochemistry. That simply means they're attached to this same face. They're on the back. It's because of the drawing. If you remember, they have to come in the same face together, and they just make this one just left over here and just putting the hydrogen group instead. They're on the same side, so we're going to call this the same stereochemistry. And also, if you redraw this one here, this is what it looks like. Okay? Because you don't normally show the hydrogen on here. So some people may think, oh, this is maybe N-type. No, because you had a hydrogen also attached to the same phase, but you just don't see it here with a hidden. So it's still same stereochemistry. This is quite common mistake you sometimes see just looking at the product right here. So, oh, it looks opposite direction. Well, metal was already there before it was doing any chemical reaction over there. So that's the type of something I want you to remember. Just one more thing is, if you look at the position here, now it's in the hydrogen group, not here, but here, right? So this is now non-Markovnikov rule here. So previously, when you do oxymercurations, you had a hydrogen group on here. It's more substituted carbon. But when you do the hydroborations, you are actually going to see your hydrogen group attached to less substituted carbon among these two. So this is more substitute than this one. This is less substitute. But you have, that's where you find the hydrogen group, unlike you saw in the different position with the oxymercuration here. So we have two similar hydration process, but the product is different because of the one that followed the Markovnikov rule, this one does not, because the way they form this dehydration. That is why I can't explain why the mechanism of this all reactions, but it's just kind of explains why you have so different products even though it's a similar hydration process. Kind of makes sense, right? Kind of makes sense. Okay. So maybe if you can do this one with something like this one, okay, here, where do you think this one will have what might be the final product? That's the kind of question here, right? Then here, this is more substitute here, right? This is less substitute, only 2. So in this case, you're going to have either this one, maybe I can do more like, or you can say, like here. Okay? If you try to do some like, well, anyway. So if that is the case, okay, which one do you think is better product from this hydroboration here? It would be this one, because you're always going to find this hydrogen group on the less substituted carbon here. This is too bulky, so the borane in the first place couldn't come into this side. So that's why this will be less substituted on the this way. So this is the right one. Makes sense, right? Just one example here. We can try to kind of apply the non-Markovnikov rule. All right, so the next one is we call this the reduction of alkene. So this is a type of bonds with the hydrogens, okay? And then they always come in the catalyst. Better catalyst is titanium and or palladium with charcoal form. Either way. So they actually just going to do reduce this one by doing, you see there's a hydrogen over here, right? So we call this hydrogenation. This is hydrogen. So the point is the why we call this the reduction. When you put those hydrogen on the carbons in the double bond, here's the thing. This is a quick review from the previous course. So whenever you have a reduction, okay, or you can say oxidation. The reduction, do you guys know what reduction is? It's gaining electron or losing electron. It's the reduction is about the gaining electrons. Okay. The oxidation is loss. They're losing electrons. Okay. So in here, we're gonna do more like specifically. So mean by that is the we're gonna use the electron density now, not just the electrons itself, like loss and gain and everything, but it's more like electron density here. So think about it. Electronegativity wise, the hydrogen is more positive than so it's a lower in electronegativity than carbon. So carbon is relatively speaking a bit more electron processing power is stronger than hydrogen over here. So when you put the hydrogen on the carbon, the carbon will have a more ability to pull more electron toward the cell, toward their directions. So that means if you're making carbon and hydrogen bond, more of this bond here, meaning your compound will be more reduced. So more numbers of carbon-hydrogen bond will guarantee that this compounds will become more reduced. Because they have the carbons and the compounds will have a more power or accessibility to the higher electron density that was pushed by more partially, relatively speaking, more positive hydrogens. Kind of makes sense, right? So the electron density is more towards this way. They have a more electron density here. It's like gaining electrons. It's not gaining electron like specific numbers of it, but it's more like electron density is a bit more higher around the carbon, pushed by the hydrogen. It's more like a relative, like a power game over there. So that is the true. Meaning it's the same thing too. If there is carbon making bond with some like oxygen, nitrogen, hydrogen, that is actually more electronegative. So if a carbon making bond with those ones, it's actually it makes lower electron density in carbon, but they're much stronger to pull the electron toward themselves. So if you have a more numbers of bonds between these ones, this will be more oxidized, right? Because they're going to pull the electron toward themselves over here. The carbon will have a lower electron density around it. So this is kind of more oxidized when you make those type of bonds. So if you break those, then carbon will be also reduced. Because there's no more higher electronegative atoms around it try to pull the electron density toward themselves. So now you have a more accessibility to the electron where previously kind of toward to the more highly electronegative atoms before. But when you break the bonds, you're also you can consider this compound more reduced as well. Like pretty same concept with this one, but the opposite way. Kind of makes sense, right? So this is why whenever you do this, whenever you do a hydrogenation, that means we have, this compound is, this alkene is reduced. So this is something you can apply. So what it happens really is quite it's not a rocket science here. If you have so we use a metal as a catalyst. We have a palladium charcoal mixture there. We have metal in the metallic ones maybe here. Okay. And then what happens to this one is the double bond with the carbons will come in, and they try to stick to the surface of the metal. They use the pi bond initially here with the had a double bond on it. And then same thing here. When hydrogen comes in a molecule, they kind of separate when they bond to they kind of stick to the metal. There's not like a specific bond there, but still it's almost like it's sticking together. And they separate in atoms too. So one comes in, then that makes here, over there. And now the surface of the metal and this the double bond is broken by making one hydrogen comes to this side and now here. And there's another hydrogen comes into this way. And now this is just not the pi bond is making, it's more like a carbon metal sigma bond like bonding. It kind of switched by the carbon and hydrogen bond again. So they are the release and this the alkene when it's done. This is how metal catalysts make this reaction much faster. So it's pretty simple process you can see on here, just the hydrogenation. Right? Okay. All right, so all right, so let's move on to oxidation now. So if you have oxidation of the alkene, it's pretty much opposite. Just say if you break the bonds with this carbon hydrogen bond, but if you try to make more bonds of this one, once again, will be oxidized. So one of the good way to do oxidation is we use the peroxy acid here. So one of the common chemical we use is the metachloro peroxy benzoic acid. This is what it looks like. Okay. Let's see. This is what it looks like. Okay. So peroxy simply means RO3 H. Okay. So you have three oxygen over here, right? 3 oxygen and 1 hydrogen, and those are this R group, this carbon here. So any of this one we call this peroxy acid here. So what it does for the oxidation is this is also quite simple too. Whenever you have this one comes in with the double bond over here, right? It's pretty much the same. They try to attack the one on the outer in the position oxygen here, and now it goes to also attack on this carbon over here. And now this double bond between oxygen and carbon will grab this hydrogen here, and that sequential movement of the electron that moves in this way. So if you redo this one here, they actually capture the oxygen and this one onto these 2 carbons. So it comes to this way. So they capture this one oxygen here. But this hydrogen grabbed by this oxygen here because it comes from the double bond and the oxygen and carbon here. So that makes hydrogen group on this carbon. But this one now has just single bond here, but the pair of electron donated here is double bond here. Okay? So now you have this one, okay? You have this one over here, and you have oxygen kind of capture like more cyclic ring kind of structure with oxygen. So we call those type of compounds epoxide. Whenever you have a kind of oxygen kind of capture in a ring position like this, we call this epoxide. So this is one good way to do oxidation. We call this epoxidation. We're simply making an epoxide compounds using peroxy acid, something like metachloroperoxy benzoic acid like this one. So this is more like all sequential reactions happening almost at the same time. They have these 2 products. The one of them will be epoxide, the oxygen capture in a more like a ring structure. This is the so you actually see there's the bond to the oxygen, which is the highly electronegative. So it is also a good example of oxidation. So that is how it works in the. Okay, so I think. Let me think. I'll just stop here today because I think I need to save some of the reactions for next Monday. So you can maybe I'll try to finish up the chapter 8 by Monday, but there's a lot of reactions you need to kind of look at and study for. So my suggestion is when you look at do you have all textbook, right? Do you have a lecture textbook, right? Yeah. So when you look at the textbook, end of the chapter 8, you actually see the summaries of the reactions and products. And there's all. So they don't show you the mechanism, but there's reactants comes with a certain reagents and then make some product there. That's all you pretty much have to know. So that would be the good summary you can just study for the chapter 8. There's a lot of things you need to kind of study for. But for your exam, mainly if you study the very last page of the chapter 8, there's a good summary of all reactions. That's really I kind of want you to study really mainly for. So then chapter 8 will be not that too long, too hard chapter to study. I can just tell you the chapter 8 I think is the longest one. Then I think might be one of the hardest chapter too. So this is a good way to study it more efficiently. So don't worry about too much. I also try to cover more on Monday, and then this should be the good way to finish the chapter. All right, thank you guys. We'll start here.